Welcome everybody to the second unit of the third week in the Parallel Programming Concepts course. In this unit we want to introduce the concept of task parallelism to you. So in the first unit we had a look on how multi-threading works in standard operating systems today, and now we want to move a little bit forward into the paradigm of task parallelism. As we already saw, there are three basic ways of dealing with parallelization in shared memory systems. The third classical way is to produce multiple processes which may share a common piece of memory or a specific region in the given memory, and based on this region they can then synchronize their work. This is a model that is only useful for coarse-grained parallelization and doesn't give you all the flexibility you may need in order to do your parallelization attempt in the code. The second mostly known concept is multi-threading, where you use the operating system concept of threads inside a process in order to get some level of concurrency, and this concurrency inside your code then may lead to a parallelization during the execution, and this hopefully brings you some speed up in the program run. The third model we now want to have a look on is concurrent tasks. And in the task model, we take the multi-threading model and elaborate it a little bit further by defining more fine-grained activities. So a task in this concept is a piece of work inside your code that is defined to be executable as a concurrent activity. So inside your code, you define as many potentially concurrent activities as possible and then hand over this task definition as part of your program to a runtime library and a compiler, and these two things in combination are then able to map the given set of tasks to some threads inside your application while it is running. The good point about that, the advantage of that, is that you become independent from the number of threads. When you have a particular level of parallelism in your hardware, so for example a 2-core, 4-core or 8-core machine, different numbers of threads are appropriate because you want to have at least one thread per physical processing element, per core for example. So you want to write your application in a way that you are independent from the number of threads and that your application becomes portable and scalable if you exchange the underlying resources. So moving from, for example, an 8-core to a 12-core machine should automatically speed up your program even further. This does not work if you have an explicitly defined number of threads in your code. This only works if you have as much concurrency as possible in your code, and then, so that a runtime system or a library can help you in putting this work on the given execution resources. This is the basic idea of the task model. You define tasks, you no longer create threads as an operating system resource, and by the definition of these tasks you give an arbitrary runtime environment or language runtime the chance to parallelize your work on the given number of processing elements. The most common example for task parallelism today is OpenMP. OpenMP is a standard created meanwhile by an industry consortium, also with collaboration from universities. And OpenMP is a specification that defines a language extension to C and C++ and Fortran. Fortran is relevant because this is one of the major languages in scientific parallel computing and is very relevant there to solve large-scale simulation problems, for example. OpenMP is a combination of compiler support and a runtime library. So in order to use OpenMP, you need a compiler, a C compiler, for example, that supports OpenMP. This is given in all major compiler products today, so whatever your C compiler is, it already should have OpenMP support inbuilt. And inside your C code, you give specific compiler instructions to the compiler to say, here is some kind of task I want to have. So you declare your different tasks, your different concurrent parts of your code by the help of such compiler pragmas, and this allows you to express your intention for parallelism, but to defer the actual implementation of the parallel execution to runtime. So in your code, you write down where you may see concurrency, where you think that multiple tasks are appropriate, and then the runtime can take all these defined tasks and run them in a parallel fashion on a given piece of hardware. So the binary you get out of an OpenMP compiled program is a binary that is a classical operating system binary as with all C code, but it has additional inbuilt code that uses the OpenMP runtime library in order to actually implement the parallelization at runtime. The OpenMP library is responsible for the thread management. So since you are defining only where you see potential tasks in your application, you no longer explicitly create threads as with the pthreads example. This leads to the fact that your runtime library, your OpenMP runtime library, decides upon the level of parallelization that is useful on the system, but you can influence this decision by the two mentioned environment variables here. So you have a chance to actually configure how your OpenMP-enabled program should behave on this or that particular piece of hardware. The programming model in OpenMP follows the so-called fork-join model. We saw that a little bit with the pthread join call in the unit before. So the idea here is again that you have a master thread that is created by the operating system that executes, for example, in C, your main function. This master thread then, by using compiler pragmas, OpenMP pragmas, creates a section that is intended to spawn multiple tasks, multiple concurrent activities. So this declaration of tasks then leads to forking of your work into different, hopefully, into different parts that hopefully run in parallel if you have the cores available. So the tasks defined in these regions are dynamically mapped to the threads managed by the OpenMP runtime library. When all these tasks are finalized, when they've reached the end of their particular code block, then there is an implicit barrier at the end. So the idea is that all the forked activities then again join together in order to continue as one serial execution stream in the master thread. You may want to do that several times, so maybe you have an intermix of parallel and non-parallel sections in your code. We talked about that when we covered Amdahl's law in the first week. So here we see that this model of forking into parallel concurrent activities and joining again is explicitly supported in the programming paradigm of OpenMP. The regions that describe your parallel work are called parallel regions, and they are somehow a wrapper for the definition of tasks inside your OpenMP-enabled program. Here you see a simple example of how such a parallel region should look like. So we have again our main function as it is common in C programs. And then we have a compiler directive, pragma OMP parallel, and this compiler directive tells the OpenMP-enabled compiler that the following code should be treated as a parallel region. So the following code should be run in multiple instances because it expresses a number of tasks. And when you run this code, you can actually see the effect that you have, in relation to the number of threads that were created by the runtime, different outputs from the different tasks being defined. Tasks may suspend at some point in time. This is part of the specification of OpenMP. The most relevant one is the implicit barrier at the end of the parallel region or explicit barrier primitives you may want to use. Since we now have a way to express parallel regions where multiple tasks can run, the question is now, how can we more precisely define the different tasks we may have in this parallel region? And in OpenMP, we have 4 basic constructs. The first one is the sections construct. So with sections, you are able to simply define arbitrary code blocks that may be dividable amongst threads. So you define arbitrary code blocks as potential tasks, and then the runtime decides if it wants to run them in parallel or not, given the existing number of threads on the system. There's an implicit barrier at the end, so if you end your sections part in the OpenMP program, all of them join again in order to continue as a serial execution stream. The second most prominent example for task definition in OpenMP is loop parallelization. So here the idea is that you have some kind of loop, for example, over a data structure, and now you want to speed up the work that is covered in this for loop by dividing parts of the loop iterations to different tasks. So if you have a loop body that is independent from the other loop body runs, yeah? So you have a loop, you have some kind of instruction that has no side effects amongst the different loop iterations, then it is possible to do at maximum all these loop iterations in parallel. But since this is commonly not the case that you have enough cores in order to do that, you will divide your loop iterations into different chunks. So if we have 10,000 loop iterations, for example, we could say the first 5,000 loop iterations are done by task number 1, while the second 5,000 loop iterations are done by task number 2. And if we now have multiple threads on multiple cores, these 5,000 iterations each can truly run in parallel, which would only take half of the time for the complete loop iteration. So loop parallelization is a very common concept in parallel programming for shared memory systems. It maps to a lot of problems. It can often be easily used by just adding the according pragmas to the for loop. The only thing you have to make sure is that your loop body iterations are truly independent from each other. The third way for defining tasks or for configuring the task creation in OpenMP is the single and master construct. This is especially relevant when we talk about race conditions that may occur. So if you have the situation that you see a piece of code that is capable of being executed in parallel, but one subpart is a true critical section, as we already discussed, then you can protect this part with single or master by saying this is a piece that should only be executed by one of the tasks at a time, or even only by one of the tasks at all. The fourth possibility to work with tasks in OpenMP is the task keyword, which similar or closely similar to sections allow you to explicitly define a couple of tasks in your code. Let's have a look into the most prominent example of OpenMP parallelization, the loop parallelization. We see here that we have, again, a compiler instruction with the pragma keyword, and this tells the compiler that the following for loop should be parallelized. We see also in the upper example that this is a combination of two OpenMP keywords, namely parallel and for. So we say two things at a time. First, that this is a parallel region, and secondly, that we want to perform loop parallelization in this parallel region. We then see an ordinary loop statement, which is the same as in all other C code. And inside the loop body, we have some complex function. This complex function, for example, here is known to be side effect free, so we can run multiple instances of this function at the same time without any problem. This would typically demand that the function has no shared data with, or global data being used. And then we have a pragma OMP critical in this example, which tells the OpenMP compiler that the following statement is a critical section. So we could use opening brackets here to do this for a whole code block, but in this case, we only protect one line of code. And in this line of code, we say the sum operation here is a critical section. That makes a lot of sense because the sum variable is a shared resource. It's a global variable, and we may have interference effects when we do this piece of code without any kind of critical section protection. So one of the interesting parts in the loop parallelization is that inside the loop body you can still use OpenMP constructs to divide amongst truly parallel activities, things that can run as parallel tasks, and things that still need some kind of synchronization. So the level of parallelization and concurrency you can formulate is very, very fine-grained, and this is the key to get a lot of small tasks and small activities that hopefully then run in parallel on your hardware and give you some kind of speed up in the overall execution. The second example shows you an advanced usage of the loop parallelization construct with the schedule keyword. The schedule keyword targets a specific problem in loop body iterations. The problem here is that your loop body is normally expected to take the same time for computation in all the different iterations. But in some cases, this may not be the case, and therefore OpenMP gives you specific keywords to configure the task creation out of loop iterations. So the easiest approach is the static scheduling approach, where continuous chunks of iterations are formulated or defined as tasks, and these tasks are then mapped to the executing threads. The good thing about such static chopping of your work is that it takes not too much overhead, so you have a comparatively low overhead for the parallelization itself. You can just do a round-robin assignment of tasks to threads, and the whole scheduling is very static. The problem is that this only works if all of your loop body executions more or less take the same time. If this is not the case, then you need another approach, and this is the dynamic scheduling configuration, where you tell the OpenMP compiler that you are aware of the fact that your loop body may take a different time according to the iteration number you have. So you basically give the compiler a hint that in your parallelization you have unbalanced load between the different tasks. If this is the case, then the OpenMP runtime will use a different strategy to actually schedule your work on the given number of threads. This brings higher overhead, but brings better results for unbalanced workload. The third more specialized scheduling support in OpenMP is the guided schedule, where you tell the OpenMP compiler that you know the fact that the first loop iterations will take a comparatively long time, while with increasing count for the loop iteration, the amount of work being done inside the loop body gets smaller and smaller. There are mathematical operations, typical parallelization problems that follow these patterns. And if you know that you have such a pattern in your code, then this schedule primitive gives the OpenMP runtime a chance to schedule your tasks more efficiently onto threads. With for loops as parallelization strategy, one of the interesting aspects is data sharing. So how can you deal with shared data, global variables, global memory inside your OpenMP program? And there are two major concepts here. One is the concept of shared variables, the other is private variables. A shared variable is something where you declare that a particular variable is used from different tasks. So the variable defined or referenced by the name should be available in all the tasks, and this is basically a tagging for the runtime. This is some kind of meta information for the runtime. It does not implement automated synchronization because this would be too much overhead. You may not need that synchronization, but it's only a small hint. The more interesting variation is the private variables part, where you tell OpenMP that a particular variable should be copied into each of the tasks. So you basically expect the runtime or the compiler to clone the variable into the different tasks in the parallel region. And this allows you to work with local data. This private variable then could, for example, live in the cache implicitly, which brings you more performance. So declaring variables as private gives you a different semantic, because each of the tasks, for example, a loop body, will have its own copy of this variable. Secondly, it also hopefully gives you some kind of optimization regarding with respect to caching. And there are different ways of initializing the value. For example, with first private, you can declare that the copied variable should have the value from the last value before the parallel region. A more general thing that turns out to be relevant when you discuss about data sharing, for example with private variables, is the memory model of OpenMP. Memory model is the idea of declaring how a language or a language extension should behave in terms of reading and writing a variable. The typical assumption you would have as a programmer is that if you write a particular global variable in one of the tasks, that this value should be immediately visible in all the other tasks for reading. This is something that we call in computer science sequential consistency. And the problem is that this is very hard to achieve, because if you do that, then you can't do any kind of smart caching approaches, for example. You really have to make sure that all the values that are written directly go to main memory, because if some other task in some other thread is accessing this value, it needs the latest value. This is a bad thing for optimization, and therefore OpenMP and many other languages come with an optimization strategy that is called relaxed consistency. So the memory model inside the language is relaxed in the way that written values may not be visible in all the other tasks immediately. So whenever you write to a variable, it may happen that another task is reading the variable later, but still sees the old value. This is an intentional behavior, since it allows to do performance optimizations, especially on the writing part. You could, for example, use a local register that is thread specific to store the variable instead of writing directly to main memory. So here we see an example for tackling the memory wall problem we identified in the first week. The price you pay for such an optimization is that you as a programmer have to deal with that fact. So you have to consider the fact that you have only a relaxed consistency model in your shared memory. So you can't be sure that written values are actually visible elsewhere. And for this reason, there's a concept of flushing in OpenMP. So there's a special primitive that allows you to make the view consistent again, to tell the compiler and the runtime, please make sure that all the values are truly written to main memory so that all the other tasks can see them. There are also some implicit flushing points, for example, at the end of a parallel region where you have an implicit barrier. Another crucial aspect of task parallelism that can be also found in OpenMP is the scheduling question. So now we discussed how tasks are defined, how you define data sharing, how you can do synchronization between the different defined tasks. But the remaining question is still, how do you map these tasks on threads? We already know that this is not done by you, the programmer, explicitly, but this is done by the runtime library. And there are two basic approaches how to do that scheduling. One approach that may be immediately clear is the central queue approach. So you have a piece of code that defines a couple of tasks in your C program, and these different tasks are now formulated by the pragmas and defined by the pragmas and put into a central queue. The central queue is a shared data structure between all the threads in your running program, and the threads are now taking tasks from the central queue and execute them one after the other. The problem with this approach is that if you get more threads on more processing elements, for example by an increasing number of cores and new processor generations, this central queue becomes more and more a bottleneck. So all of the threads running on the different processing elements need to access the shared resource, the shared central queue, in order to get their work. And this, after a while, becomes your serial portion in Amdahl's law, your bottleneck, and then you get problems with the parallelization optimization. For this reason, there is an alternative approach for task scheduling in this environment, and this is the work stealing approach. Work stealing in OpenMP and also in other libraries has the idea of defining no longer a central queue of tasks that should be executed, hopefully in parallel, but a task queue per thread. So for each thread running normally on a core, you define a local task queue with stuff that has to be executed, and the runtime library makes sure that initially all the different queues are filled with a couple of tasks so that the spawned threads during the execution can run all these tasks in parallel on the given hardware. When you now have the situation that some tasks are not balanced, so that maybe one of the queue becomes faster empty than the other one, then the concept of work stealing kicks in. Work stealing means that a thread that has an idle task queue is enabled to take task work from other threads, from their queues, into its own. So it steals actually the task to be executed from the overloaded thread and puts it into its own work queue. This is implemented in a way that the stealing of tasks and the local work of the thread that is already overloaded does not influence each other, because tasks are taken from the top of the queue, while the fresh work for the thread is taken from the bottom of the queue. So as you can see here in the picture. So the basic idea of work stealing is that you have a scalable approach of scheduling tasks on threads, because if you now create more threads on more processing elements, you still have only the problem of mutual synchronization between the thread that is stealing some work and the thread and its queue that has the according work available. This is a well-known approach that scales pretty good in parallel environments and shared memory environments, and is therefore meanwhile implemented in all task parallel frameworks that are available in practice.